Have you ever looked up at the night sky and seen a tiny point of light moving way faster than any airplane? Well, chances are you were looking at an artificial satellite. But it begs the question, right? How did these objects, some as massive as the International Space Station, just stay up there? How do they orbit the Earth without constantly firing engines to keep from falling? The answer isn't magic. It's a really elegant balance of physics, and that's exactly what we're going to break down.
So here's our game plan. We'll kick things off with some basic definitions to make sure we're all on the same page. Then we'll get into the tricky business of actually getting into space. After that, we'll dive into the core physics of what keeps a satellite in orbit. We'll even look at the math that makes it all work, before wrapping up with some awesome real-world examples.
All right, first things first. Before we can talk about how orbits work, we really need to nail down a solid definition for what a satellite even is.
So at its core, a satellite is simply any object that's circling a planet. And the crucial part here is why it's circling. It's not held up by some mysterious anti-gravity tech. It's held in that stable path, that orbit, purely by the force of gravity. That's it.
Now, when we say satellite, we're usually talking about one of two kinds. You've got your natural satellites, think of our moon. It's a huge celestial body that was just captured by Earth's gravity a long, long time ago. But then you have artificial satellites. These are the ones we build and launch ourselves for all sorts of reasons. Communication, GPS, weather forecasting, you name it. Okay, so we know what a satellite is, but that brings us to the next big question. How in the world do we get one from the ground all the way up into a stable orbit? It's a real balancing act. To really get this, let's do a little thought experiment. Imagine you're standing on top of a mountain that's so tall it pokes out of the atmosphere, and you have a cannon. What happens when you fire a cannonball horizontally? Well, the answer depends completely on how fast it's going. So let's say you fire it, but not very fast. What happens? Gravity immediately starts pulling it down. The cannonball travels in a curve, for sure, but that curve is way too steep. Gravity wins, and it just crashes back down to Earth. No orbit for you. But what if you could fire it at exactly the right speed? A very, very high speed. Well, then something incredible happens. The path the cannonball follows, its curve downward, perfectly matches the curve of the Earth itself. It's constantly falling, but it's also moving forward so fast that it literally keeps missing the ground. And that, my friends, is what an orbit is. Of course, you can also overshoot it. If you fire that cannonball with way too much speed, its path won't curve down enough to stay in a nice circle. It'll swing out into a big, stretched-out elliptical orbit. And if you give it enough oomph, what we call escape velocity, it'll break free from Earth's gravity completely and just fly off into deep space. Okay, that thought experiment gives us a great picture of the launch. Now let's get into the nitty-gritty physics, the constant tug-of-war that keeps a satellite perfectly balanced in that orbit. This is really the heart of it all. You have two forces, or rather one force and one property of motion, in a constant battle. On one side, you've got inertia. That's just the satellite's tendency to keep moving in a perfectly straight line forever. But on the other side, you have the relentless, constant pull of Earth's gravity, trying to yank it straight down. A stable orbit is what happens when those two are in a perfect deadlock. I absolutely love this quote because it sums it up so perfectly. A satellite isn't fighting gravity, it's using it. Gravity is providing the exact amount of force needed, the centripetal force, to continuously bend the satellite's straight-line path into a perfect circle. So yes, it is in a state of perpetual freefall. It's just falling around the Earth, not into it. So, we get the concept now, right? This beautiful balance between wanting to go straight and being pulled into a curve. Now let's see how physics allows us to describe this with the precision of mathematics. That just right speed we keep talking about, it has a name, orbital velocity. It's the very specific speed an object needs to be traveling to maintain a stable circular orbit at a certain height. Go any slower, you fall. Go any faster, and your orbit changes from a circle to an ellipse, or you fly away entirely. So how do we figure out that magic number? Well, the math is actually pretty straightforward. We start with two things we already know. First, to make anything move in a circle, you need a centripetal force. That's step one. F equals mv squared over r. Second, what force is pulling our satellite into a circle? It's gravity. That's step two. So since gravity is the centripetal force here, we can just set the two equations equal to each other. When we solve for v, the velocity, something really interesting happens. Notice how the little m, the mass of the satellite, is on both sides? It cancels out. This is huge.
It means the orbital velocity doesn't depend on how heavy the satellite is at all. It only depends on the mass of the planet, m, and the distance from its center, r.
All right, that equation is incredibly powerful. Let's put it to the test and see how it applies to some real-world satellites zipping around above our heads right now. Let's take the International Space Station. It orbits at about 400 kilometers up. If you plug that altitude and Earth's mass into our shiny new equation, you get an orbital velocity of 7.66 kilometers per second. Let that sink in. That's over 27,000 kilometers an hour. It's so fast that it circles the entire planet about 16 times every single day. This table really breaks down the two big takeaways from our formula. First, as you go higher up, as your altitude r increases, the orbital speed you need actually goes down. It's an inverse relationship. This makes sense, right? The farther away you are, the weaker gravity's pull is, so you don't need to be going as fast to stay in that balanced orbit. Second, the more massive the planet M is, the faster you have to go. A bigger planet has a stronger gravitational pull, so you need a much higher speed to counteract it and avoid getting pulled down. And we see this everywhere. The Hubble Space Telescope is a bit higher than the ISS, and just like our formula predicts, it travels a little bit slower. Then you have extreme cases like Voyager 1. It was launched so fast that it completely beat our sun's gravity and is now the farthest thing we've ever sent out, cruising through the space between stars. So let's leave you with a final thought to chew on. We know now that a more massive planet needs a faster orbital speed. So just imagine how different would the orbital mechanics be for a satellite trying to circle the giant planet Jupiter compared to one orbiting tiny Mars. It's a direct application of the physics we've just walked through.